At the turn of the 19th century, physicists were confronted with some troubling problems. These originated in a couple of experiments which not only did they struggle to explain, but they also disagreed with theories and equations they worked with at the time. These two problems spelled out the rise of quantum mechanics, the study of the behavior of elementary particles and other small pieces of matter. But these problems also spelled the downfall of classical physics. The first problem came from the amount of thermal radiation that a heated object would emit. As you might know, all things radiate heat in the form of electromagnetic waves. Usually these waves are in infrared, so you can't see them. But if you heat objects up to higher temperatures, they will start to radiate heat in the form of visible light, such as a red-hot piece of metal or glowing coals in a fire. Now the problem wasn't so much about the pretty colors they would turn into. The problem concerned the amount of thermal radiation that they would emit. Experimental results did not agree with any theory that physicists had already cooked up. That is, until Max Planck came along. Max Planck had worked with this problem for quite a while, and he was so frustrated with it that he basically threw all the known explanations, equations, models, and theories out the window. In his own words, I can characterize the whole procedure as an act of desperation. Max Planck came up with a new equation that fit the experimental results perfectly. The theory that came with the equation was that there's a minimum amount of energy that an electromagnetic wave has to carry, and that this minimum amount of energy is proportional to the frequency of the wave. What happens is that the electromagnetic waves carry a certain number of packets of energy called quanta, and these packets contain the minimum amount of energy that the wave has to carry. The book The Elegant Universe by Brian Greene has a great analogy for this phenomenon. Imagine you have a room full of employees who are waiting to get paid in cash, except that these employees are special. They will only accept specific bills of money. The guy on the left will only accept €5 bills. The guy after that, only €10 bills. After that, only €20 bills. And the last one will only accept €50 bills. All of these employees all have a salary of €60. So when you pay the first guy, you have to pay him 12 €5 bills. The next guy, you pay 6 €10 bills. The one after that, 3 €20 bills. But then you get to the last one. He only accepts €50 bills. You can't give him 2 €50 bills because you'd be paying him €40 too much. So you come to the conclusion that you will just pay him one €50 bill and that he should just deal with it. You can imagine all these way too picky people as electromagnetic waves of different frequency. The €5 bill guy would be a low frequency electromagnetic wave, while the €50 bill guy would be a high frequency electromagnetic wave. The bills that they accept are the minimum amount of energy that they need, and their salary, the €60, is the total amount of energy that there is. As you can see with the example, it is harder to get high frequency electromagnetic waves because the minimum amount of energy that they need to have one packet of energy is very large. Soon after the discovery of Max Planck, the soon-to-be famous scientist, Albert Einstein, used the theory to explain the photoelectric effect, a phenomenon whereby certain metals eject electrons when you shine a light on them. He made the connection between how light is quantized, that is, are made out of minimum amounts of energy, and how the amount of electrons ejected by the metal depends on the frequency of the light, not the brightness. He said that, since the number of ejected electrons depends on the frequency of the light, when, for example, the frequency was too low, the packets of energy carry too little energy to excite the electrons enough for them to shoot out of the atom. However, as the frequency increased and the amount of energy the packets carried increased as well, more electrons were given enough energy to eject out of the atom. Not only this, but Einstein also said that since the electrons were ejected instantly after they were hit, that light must be made out of particles. This is important information for later. Keep it in mind. Anyway, Niels Bohr, another important pioneer in quantum physics, also made a big discovery that had to do with Max Planck's theory. He solved the second big problem that I talked about in the beginning, by suggesting that not only electromagnetic waves are quantized, but that matter is quantized as well. Now, you might think that's ridiculous, but as you will soon see, his theory is quite a sound theory. When you heat up certain gases in a container, they will start to give off a certain color. They will become fluorescent. And the weird thing is that if you shine the light that it gives off through a prism, you won't get a nice rainbow as you do with normal white light. Instead, you will get very distinct lines of very distinct colors. Why did it do that and not give a continuous spectrum of color? Bohr explained this by using the theory of Max Planck. He said that electrons orbited around the nucleus, but only at very discrete orbits. Electrons, just like electromagnetic waves, had a specific minimum amount of energy which could not be divided. This meant that the electrons had to have very specific energy levels that they were allowed to be in. Nowhere in between. This is like the fussy employees with the money. The guy either had 5 euros or 10 euros or even 15 euros, but he did not have, say, 7 euros or 11 euros. It's not allowed. So what did this mean for the actual experiment? Bohr said that when you heated up the gas, the electrons in the atoms of the gas got all excited, and some of them got enough energy to jump from one energy level, or orbital, to a higher energy level. Then, when the electron calmed down, it would jump back down to a lower energy state, and in the process would emit energy in the form of an electromagnetic wave, in this case, visible light. The color of the wave, aka the frequency and thus the energy that the electromagnetic wave carried, would directly depend on how far the electron jumped. So if the electron only jumped a bit, it would give off red light, and if the electron jumped a large distance, it would give off blue light. The trippy part is that the electron basically teleports from one energy state to the other. It doesn't move through the space in between. If it weren't for this kind of teleporting, you would see a rainbow of light as the electron moved from one energy level to another. But that's not what we see, and that's also not what happens. This weird phenomenon is called a quantum leap. Let's move on from how light and matter are quantized to another amazing part of quantum mechanics, namely wave-particle duality, and the experiment from which it came from, the dual-slit experiment. The double-slit experiment is quite a famous experiment, at least in the scientific community, in which you shine a light through two narrow slits. The experiment was designed and first performed by Thomas Young in 1801, and it was used to bring an end to the raging debate that was going on at the time about whether light was made out of waves or particles. If light was made out of particles, what you would see is that light would go through the two slits and make two bands of light on the screen behind the slits. However, that's not what you see when you perform the experiment. What you see are lots of bands of light that spread across the screen behind the slits. The bands of lights appear even in places where you would expect the light to be blocked by the slit. This is a characteristic of waves. So the original double slit experiment proved that light was a wave, not a stream of particles. However, the interesting part would come much later when scientists did the same experiment but with electrons instead of light. What they did was that they shot electrons at the slits one by one and recorded with a detector where they landed. After shooting tens of thousands of electrons, what they got is a pattern similar to that of light. They got the same interference pattern. How could this be? How could you get the pattern that you get with waves with a particle? Well, you can't. Unless, of course, you give up the idea that it is a particle. Because, tell you what, electrons are both waves and particles at the same time. So this is where the stuff really gets weird. Quantum mechanics tells us that these rules apply for all fundamental particles. But we'll just be sticking to electrons for our explanation. Until the position of the electron is measured, aka as the electron goes towards and through the slits, it is something called a probability wave. One can imagine a probability wave as a normal wave, except that here the wave shows where the electron is most likely to be. Places where the wave has a high magnitude is where there's a high probability of finding the electron and vice versa. It is important to note that where the wave is the biggest is not where most of the electron is, but instead where the wave is biggest is where the electron is most likely to be. What this means is that, like a normal wave, as the probability wave goes through the two slits, it undergoes diffraction and interferes with itself, creating positive and negative interference. This creates the same interference pattern on the detector as a normal wave, except that when the wave reaches the detector, the electron is forced to choose a position, and that is where the detector detects the electron. After repeating this and doing the same thing with thousands of electrons, even if they are fired one by one, you would get an interference pattern where the percentage of electrons at any given place is almost the same as the probability of them being there. Quantum mechanics tells us that everything in the universe is both a particle and a wave. Yeah, everything. From electrons, to tables, to your computer, and to you and me. However, the wavelength of an object corresponds to the momentum of that object. This leads us straight into our next topic, Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is probably one of the most famous principles of quantum mechanics. Werner Heisenberg, the guy who discovered the principle, no surprises there, stated what the principle is very simply. The more precisely the position is determined, the less precisely the momentum is known in this instant, and vice versa. This is the simplest way of describing the principle. However, nobody can begin to understand the implications of the uncertainty principle from just hearing that statement. Let me explain in more detail. The uncertainty principle arises from the fact that everything in the universe acts like a particle as well as a wave. In quantum mechanics, the concepts of exact velocity and exact position do not exist. Quantum mechanics tells us that in nature, a particle literally cannot have a definite velocity or definite position. You can get a very good idea of one or the other, but not an exact measurement, and definitely not of both at the same time. More specifically, the better you know the value of one of them, the more uncertain the value of the other becomes. The way it works can be described with an example. You can measure the position of a particle, such as an electron, by bouncing electromagnetic waves off them. The photons will hit the electron and then bounce back, showing you where the electron is. However, if there are a lot of photons hitting the electrons, they will disturb the velocity of the electron. Of course, if you want to decrease the effect on the velocity, the logical thing is to decrease the amount of photons you bounce off the electron. And this works, except that there is a limit. You have to bounce at least one photon off of the electron. But remember, Max Planck told us that the wavelength of a single photon is proportional to its frequency. So we just increase the wavelength to decrease the amount of energy that the photon carries. This, however, will still not work to measure the velocity and position of the particle. The information about the position of an electron has a margin of error that is equal to the wavelength of the photon. So with a long wavelength, you know that the electron is somewhere there, within the boundaries of the wavelength. So that is the problem. You can determine the position of the electron very well with a short wavelength, but then the energy of the photon affects the velocity of the electron. On the other hand, you can measure the velocity very well with a photon, but that has low energy, but then you don't know the position well because the wavelength is very long. You also cannot know the exact position of the electron because then you would need a wavelength of 0, aka no wavelength. And you cannot know the exact momentum because you would need a photon to have no energy. Einstein didn't like this uncertainty principle and proposed that although we cannot know the exact position or velocity, or know both the position and the velocity accurately at the same time, the particles still had an exact position and velocity. We just couldn't measure it. However, his proposal was to be disproved by another experiment. If you put an electron in a solid box and started to make that box smaller and smaller by moving the walls of the box inward, you would know the position of the electron more and more accurately. However, as the box gets smaller, the electron will move increasingly with unpredictable speed. The book The Elegant Universe describes it as if it were overcome with claustrophobia. Now, to round things off, I would like to tell you how quantum mechanics relates to your life. Why should you care about quantum mechanics? I can think of a great reason. The computer you're watching this video works thanks to quantum mechanics. In fact, our digital age is all thanks to this crazy theory, because with it, we learned how to make things like transistors, diodes, and all these other tiny things that control the flow of electrons. Nanotechnology and chemistry have both been heavily influenced by it. So you owe a lot of your life, or at least I owe a lot of my life, to this crazy theory that barely makes any sense, but that is so good it hasn't disagreed with experiment once.
Don't look at me like that with your eyebrows. So I'm like, silence!